Hello everyone and welcome to a lesson of physics. In this video I'm going to solve some of the sample question 2 of practical paper of AS Physics. The thing is, if you want a detailed video on how to solve question number 1, you can watch the video for which I have given the link in description. If you haven't watched the video for question number 1, this is the first thing that you should be doing, because question number 1 as important as question number 2, especially because you have to draw the graph, you have to find some of the values in that, and you have to find the gradient, you have to find the y-intercept. I've uploaded a detailed video how to solve question number 1. I've explained how to draw the graph, significant figure, decimal places, and all that. So you can just get the link in the description and it'll take you there to that video. But here for this one, we're going to look at some of the important concepts and some of the most frequently tested concepts for question number 2 of practical paper. In this video I'm going to solve question number 2 of practical paper of AS Physics, and more importantly we are going to discuss some of the repeatedly asked questions, because you have to follow the same pattern for many of the parts of this question. So we are going to discuss some of the repeatedly asked questions. So let's take a look at the first one. You see, one question that you're always going to get in question number 2 is estimate the percentage uncertainty. And it could be in force, it could be in length, it could be in diameter, it could be in time period. So you have to estimate the percentage uncertainty. Now this is a question that many of the students, even the good ones, many of the students attempt this one incorrectly. Now first of all, there are two methods to answer this question. The first one is if you guess the absolute uncertainty for the given value, which is the rule of thumb is, let's say you're measuring the length and the normal absolute uncertainty is 0.1, but in this case you have to take the absolute uncertainty 2 or 3 times more than the actual uncertainty. This is one of the method. The second method, and the method that we recommend, is that you solve the previous question, the previous part, in such a way that you take 2 or 3 readings. In matter of fact, the previous question is generally for 2 marks, and hence you have to take more than 1 reading for whatever quantity is asked for the previous part. For example, in this question they ask you for the force which is needed to just make the block move. So what do? Take the first reading of force. Let's say the first reading was 2.2 newtons. Then you take another reading, because you cannot be really sure about that. So let's say we take another reading and then we can take another one, but at least you have to take 2 readings. 2 would be fine. What do you do afterwards? Once you have taken 3 readings, then you take the average value, and that would be your actual value for F0. So the average of these 3 would be 2.0. So you write 2.0 over here. So this is how you answer for the first part. And this is the only way that you're going to get 2 marks. If you take a single reading and you write it down as it is, you're going to get only 1 mark. So just to be on safe side, take 2 readings, at least 2 readings. Up next, you have to estimate the percentage uncertainty in your value of F0. So how do we solve this? The first thing is you would be writing down the formula for the percentage uncertainty. That would equal, or you can simply write percentage uncertainty in F0 equals absolute uncertainty, which is represented by delta F0. Okay, you may not be using the symbols. You can write absolute uncertainty, just you can write in description, divided by principal value, which is F0, times 100. Now before you insert the value of absolute uncertainty, there you have to make use of the multiple readings that you have taken previously. And if you take a look at the previous readings, what you do afterwards is you note down the maximum reading. For example, this one was the maximum and this one was the minimum. And then you find delta F0. You find absolute uncertainty by this method, which is maximum minus minimum, which is also known as range divided by 2. So what was the maximum? 2.2. What was the minimum? 1.8. And this thing divided by 2. So 0.4 divided by 2 would be 0.2. So your absolute uncertainty is 0.2. That's the value of delta F naught. Now you insert this value in the formula. So 0.2 divided by the principal value 2.0 multiply by 100. Then you hit it on the calculator as it is. And this is the standard way that you can estimate the percentage uncertainty in question number 2 of paper 3. And this method is compatible for each and every situation. The other question that could be there, what if you're getting similar readings? Like first time you have taken a reading, it is 2.2. Second time you have taken a reading, it is again 2.2. And let's say third time it is also 2.2. What do you do in that case? And the answer to that is just change the readings. Just change the readings off camera. You don't have to be vocal about it. Just do it without telling anyone. Let's say, so what you do is, let's say the first reading was 2.2 and the second one. And this thing is, this generally happens when you are measuring the diameter of a wire or something, of a coin. If you're measuring the diameter of a wire, diameter of a coin, then there is a chance that you might be getting same reading. So then in that case, what you can do is simply change one of the reading. So here I have another question which is related to this thing. So for example, in this one question over here, you have to determine and record the radius r of the suspended mass hanger at its widest point. So once again, this question is for 2 marks. And the follow-up question is, estimate the percentage uncertainty. Now, let me write down the formula for percentage uncertainty in R. So percentage uncertainty in R equals to absolute uncertainty divided by the principal value of R times 100. But in order to have the reading of absolute uncertainty in R, I have to have at least 2 readings of radius. So what do you do in that case? So the answer to that is, when you were noting down the value of R, you were calculating the value of R, you have to take at least 2 readings. So let's say the first time you have taken the diameter comes out to be, let's say 3.8 centimeters. Hence the radius would be 1.9 centimeters. And the diameter next time that you take it once again, so you can have different values of R. This time the diameter comes out to be 4.0. And then you work out the radius, and radius in this case would be 2.0 because radius is half of the diameter. And if you're getting, once again, like I said, if you're getting the same reading, just change one of the reading. You'll be fine with it. So what is the radius now? You take the average value, add both of them, divide them by 2, and you'll be writing down the average value over here. After that, once you have to find delta R, what you'll do is, this is your maximum value of radius, this is your minimum value. You do maximum value minus minimum value divided by 2. This would be your delta R divided by whatever the average value was, multiply by 100. So whenever you have to find percentage uncertainty, especially when they ask you to estimate the percentage uncertainty, keep it in your mind the question, in the previous part, whatever measurement you have taken, you have to take at least 2 measurements, and those 2 measurements should be different. And if they're not different, if you're getting the same readings, just change one of the readings. So if you answer the percentage uncertainty question this way, the first part and the second part, you'll never get it wrong. So let's move on to the next thing. When they ask you to find the time period, you are required to take time of multiple oscillations, at least 10, and it depends on the question, depends on the situation. If the oscillation, if you're not getting enough oscillations, for example, if you get into a situation where you're not getting more than 5, more than 6, 7 oscillations because the object stops moving, then you're fine with 5 oscillations as well. So what I can do in this case is I can make a time of 10 oscillations. Let's call it T1. Time of 10 oscillations could be, let's say, 10.2 seconds. And then I find the time period, which would be 10.2 divided by number of oscillations, which in this case would be 1.02 seconds. The other rule is, which is very important, whenever you're taking a reading through an instrument, you have to be careful with the decimal places. Whenever you take a reading through an instrument, through an apparatus, you have to be careful with the decimal places. And for stopwatch, we are fine with 1 decimal place. No need to go beyond it. You can go with 2 decimal place, but 1 decimal place would be fine. So stopwatch, for time, 1 dp would be fine. And for length, whenever you take a reading through a meter rule, okay, the most commonly used one, meter rule, whenever you take a reading through the meter rule, it has to be to 1 decimal place in centimeter. So for example, you get a reading 5 centimeter, you don't write it as 5 centimeter, you write it as 5.0 centimeter. The other thing is, once you calculate a reading, a value through a calculator, through calculation or through calculator, in that case you be careful with significant figures. You don't worry about decimal places. After you use the calculator, you worry about the significant figures. Now for example, this reading was obtained through the stopwatch, and that's why the reading is to 1 decimal place. And the reading, the value capital D was obtained through the calculator, and that's why I'm not worrying about the decimal places. Rather, I must be having the same number of significant figures compared to raw data. Raw data has 3 SF, so capital T, which is obtained through the calculator, must also have 3 SF. So calculator, significant figures, and apparatus or instrument, decimal places. And then in question number 2, they always ask you this part in which you have to perform the same stuff. You have to go take the same readings but for different values. For example, they say in this part, remove the 100 grams mass hanger and replace with a 50 gram mass hanger, and you repeat all the previous parts as it is. So for example, A2, B and C. What do we find in A2? This is A, this is 2. We were finding R, the radius, and then the time period, and then C, which is obtained from this formula. You don't have to memorize formula on your own. That would be given on the question paper. So you do the same process but for different values. So you'll have to replace the apparatus. You'll have to change some of the stuff through your apparatus and replace with some of the new one. And finally, once you're done with this, you will be having 2 sets of values, or I should say 2 sets of data. One over here with the previous values of mass and all that, and the second set of data you get over here once you replace 100 grams mass hanger with 50 gram mass hanger. And once you have found these 2 set of data, they always ask you this question: find first value of K and second value of K. So what do you do in that? So K, if I make K the subject, K equals to T square over C, and K equals to T square over C, because we have to find 2 values of K. The first value of K would be obtained through first set of data. When you were using 100 grams mass hanger, what was the value of T over there? For example, the value of T from here, the value of C from here. That was the first set of data, and from here you get the first value of K. And the second value of K would be obtained through the second set of data. Once you replace a 100 grams mass hanger with 50 grams mass hanger, it could be anything depending on the question. But once you remove the first apparatus and replace with the new one, then you get second set of data. From there you can find the second value of k. And the follow-up question is, they always ask you this one: explain whether your results support the suggested relation in E1. They always ask you this one. So for this one, first of all, you have to write down the formula delta k, which is the difference in the two values of k, the first value and the second value, bigger minus smaller, divided by k average. You can also divide by first value, you can also divide by second value, and you can also divide by average value. Multiply by 100. This gives you the percentage error. And if the answer to this expression is, let's say, 25%, then you say, after you set a criteria, you say, since it is, or the error is beyond 20% of experimental accuracy, so it doesn't support. You have to mention the criteria. You can also go with a criteria of 15%. You can also go with a criteria of 25%, 30%. But whatever criteria you have set, you go with that. So if you say that we are setting a criteria of 20%, if the answer is in the criteria of 20%, for example 18, 19, 17, 16, then you say, okay, the results support the suggested relation. If it is more than 20, you say it does not support the suggested relation. So how do you find delta k? Once again, delta k has to be written with a positive sign. So you have to write the bigger value, then subtract the smaller value from that. If the first value is greater, then write k1 minus k2. If the second value is greater, then do k2 minus k1 divided by average value. How do you take the average? First plus second divided by 2. And in order to convert it into percentage, you multiply by 100. And for the last one, describe 4 sources of uncertainty or limitation of the procedure for the experiment. You do have some of the standard sources of uncertainty which you can write pretty much with all the experiments. For example, the first source of uncertainty you can write is 2 values of k are not enough to draw a valid conclusion. And you can always write the way to improve this: take more readings and plot the graph. Then you can see which 2 quantities were used. For example, in this one we were comparing t and c. So t or c square, I think, or t and c, t square and c. Then you can say draw the graph of t square and c. But this is the standard one that you can write with pretty much all the experiments. And the other sources of uncertainty, once you perform the experiment, you'll find those, so you'll encounter those sources of uncertainty. What you can do is just keep noting down whenever you encounter a source of uncertainty while performing the experiment, instead of leaving it at the final stages. If you say there is the mass connected to a string, it is not balanced, it is not vertical, it keeps moving, that's why you're not able to take the reading for the length, just note it down over there instead of leaving it for the final part.